各位同学啊，各位同行，各位田径大家好。早上不好意思，因为有一些事情没有办法来跟大家开个场。那我是台湾中心学文技术组组长王玉琪。那今天很欢迎大家来参加这个 ADCP 的算是教育训练，也是一个交流的一个机会。那等一下我们会请英国来的演讲技师，接着介绍下午的课程。那下午的东西非常多哈，所以他就赶快请大家进来，就开始今天的课程。OK， welcome Mr. Dr. Lee. Okay, he's from England, and then please speak it slow. Because
English people speak too quick. Okay. Remind me, because it is late. My mind is going quick. So tell me slow.
Okay. And we all use the American accent.
Okay.
I stayed 1 year in UK, so I know the accent is very different.
It is quite different.
So Lee, could you switch to American accent?
Can you
change to American accent?
Actually, the word is English.
Okay, let's welcome Dr. Lee.
Thank you. I do so apologise for being so late. Flights around the world are just, you never know, and I'm really sorry. I'm also very aware that some of the things I will talk about, Mark will also have covered. If you're very happy with it, and we don't need to talk about it, if somebody can just sort of say, move on, okay, and then we can make sure we cover the more important things that you're less familiar with. Okay, but I will just go through the presentation I have got, because I think there's a little bit of structure to it. Could you just, who's not used the instrument at all, or even just used it a little bit? How many, hands up if you've not used the instrument? Mark, hands up. So everybody has used the instrument at some stage. Okay? Okay, good. So we can get away with some of that. Myself, I've worked for SonTek for 13 years. Prior to that, I worked for the UK government as a field hydrologist. So my 27 years of hydrology experience is really field data collection. That is my expertise. I am on the International Standards Committee for velocity area methods, which includes the Doppler instruments, because of my experience in the field. Not because I'm an acoustic engineer, not because I'm a mathematician, I'm not. I'm a field hydrologist, and that's where my basis comes from. I take the point of view, if we do a good measurement at the correct place, we won't have any problems with the data. I know that's not always true, but if we try to achieve that, the better we make our measurements in the field, the better our data, the less work we have to do afterwards. But we will talk about the problems as well. Just a few slides on different things. So SonTek make ADCPs and ADVs. We make acoustic Doppler current profilers and acoustic Doppler velocimeters. High precision, high sample rate for the ADVs, and much more general sort of data collection profiling with the ADCPs. And they get used from tiny little streams that are 20 centimetres wide to rivers that are maybe even 20 kilometres wide. Here we see an ADV up in the top corner, just being used for a tiny stream. The discharge in that stream was around about 4 litres per second. Down in the bottom corner, a continuous monitoring. This is a mountain stream near to where I live in the UK. This is an irrigation canal in India. This was actually a breakthrough moment for SonTek, or for the industry. It doesn't matter whether it's SonTek or the industry. ADCPs have always been really good at doing big rivers, wide rivers, quite deep and fast flowing. When they start going slowly, the data becomes hard to collect with high accuracy. The M9 changed all of that. With the previous instruments, we would never have been able to measure this canal. 3 centimetres per second, the water is flowing. It's really slow. And it's about 4 metres deep. Okay. An ADCP would have given really poor data 6 years ago in that situation. Now we can, with hand on heart, say the data coming that they get from this section would be really good. The M9 that you have here it's a really wonderful instrument. It works as well. This channel at the top is 2.4 metres wide, 40 centimetres deep. Okay? It works as well in that channel as it does in the Amazon at 3 kilometres wide, 60 metres deep. Well, yeah, 60 metres deep. We'll explain a bit more about why I said 60 metres later. It gets used up in the Arctic Circle. Drill a hole in the ice, put the instrument through the ice, okay, and measure the flow going underneath. It's a really flexible, highly accurate piece of instrument. And just different forms of deployment. I'll spend quite a bit more time later on different forms of deployment. So just different shots from around the world. This one here, at the beginning of April, I was in Nepal, in Kathmandu, 2 weeks before the earthquake in Nepal. And this is the main river running through the centre of Kathmandu, the Bagmati River. So I was very grateful that I was not there 2 weeks later. These people are sort of using the ADVs here. They were trying to clean up the rivers. And while I was there, they were saying Kathmandu is overdue an earthquake by many years. So it was quite scary. And they actually said the best thing to clean up the rivers in Kathmandu would be for there to be an earthquake, and that they could then start again. So I don't know that they actually meant that. That's what they got. So we'll move on from that. So some of you have the M9, and some of you have the S5, yes? Is that right, Mark?
There's one gentleman with the
One S5.
He's an irrigation customer in the north.
Okay, so I am primarily going to talk about the M9, but please, much of it is relevant, of course, to the S5. Please, if you have any particular questions, please do ask. The difference between the two is that with the S5, we have 5 beams, 4 measuring the water velocity as well as the depth of the bottom track of 3 megahertz, and 1 of 1 megahertz measuring the depth directly beneath the instruments. And then we have the M9 with 4 of 3 megahertz and 4 of 1 megahertz and at 500 kilohertz to measure the depth. The beauty of the M9 is it actually works as well, or even better, in shallow water than the shallow water S5 does. And we'll talk about that more later. Here we have that the Amazon River that I was talking about. So we have left hand here 0 metres up to 3,500 metres here, 3.5 kilometres. Just over 60 metres deep, the channel. discharge of 146,000 cubic meters per second. It wasn't even a flood, this is just normal conditions. We say that the M9 works to 40 meters. All our brochures say it will work from 30 centimeters to 40 meters. Here we have data to 60 meters. Why? Because acoustic conditions means that actually, you know, what that number we're given is just an average, really. In good acoustic conditions, fresh water that is warm, that has a nice sediment in it, we get good propagation of the acoustic signal. If we go to the other side of it, we have seawater that is very cold and is very clear. We would not get anywhere near the 60 metres. We would probably not get anywhere near the 40 metres. I went to one site in Scotland and I got velocity data to 12 metres only with an M9. Very cold, saline water and very clear. It then goes around again if the water is too laden with sediment, which is, I know a situation you're going to get over in Asia.
Can you mention Nisi? Because we say you in the scale. Nisi, the monster.
Yeah, I will mention Nessie, yeah. Yeah, Nessie, we'll come back to it. There might be a picture of Nessie later. Yeah, once you get too much sediment, the sound cannot go any further. All the sound becomes absorbed by the sediment, and then we lose range again. And again, we'll definitely talk about that later in specific instances. But I just want to put a few ground facts down so that we're thinking about the way that the instrument works and some of the problems and some of the benefits that we will have. Okay, we'll talk about that in the rush. These instruments, they will work directly off of a power supply. So if we're on the boat, we have a cable here, and we can plug this one into a power supply. We can plug this straight into the instrument, straight into our PC. You've done this.
Yeah, done this, yeah.
Thank you.
Yeah.
Done that.
Yeah.
Tablet.
Yeah.
Good. So we don't need to talk about the second mark. We'll come back into GPS in a bit more detail later.
Okay, yeah, do
This is just talking about different dates. We'll come back to this. Okay. I want to make sure that Mark told you the truth on later. I'm sorry, it's my field hydrology side. Okay. So we're going to talk about making a measurement, whether it be in a river, a lake, some form of channel. Before we go out there, we've got to decide what is our data requirement, because it then changes the way that we take the measurement and where we take the measurement. Okay, and why we would. Okay. So what is the main reason that you all want to use the M9? Is it discharge? Is it to make a flow measurement? Yes? If it is, that's good news, because the RiverSurveyor was designed as a discharge measurement instrument. Okay? We have a number of researchers who find the M9 frustrating in that it's collecting so much wonderful data, but it's hard to get that data out. And I'm very much aware of that problem. And the more people I meet who tell me what the problems are, the more I can tell our R&D team, this is what you've got to do to change it. So if you're seeing a weakness in the way that we do things, we want to talk about that as well. Okay? I don't know them all, because I'm not a researcher, I've never been a researcher. I've always been a hydrologist, going out and collecting discharge data. Okay. And that's, as I say, what the M9 has been designed to do. Okay. What are the water conditions? We've got to think about this. Are they slow moving? Are they fast moving? Are they deep? Do they vary a lot? Is it rapidly changing? It all changes the way, do we just take a very quick measurement, a nice, easy, straightforward measurement, or in a fast changing flow, we might sort of decide we've got to very quickly go across the river and take that measurement. It changes the way how we deploy the instrument, where we can deploy it from. Do we have access to just to the river banks? Are we thinking that we're going to use a bridge? Are we going to use boats? Once we've made those decisions, sort of understood what we're needing to do, where we're going, we can then choose the method of data collection. Whether it be sort of the moving boat method using RiverSurveyor Live, a stationary method, whether we're just doing a survey, okay, where we have the HydroSurveyor, where we do a bathymetric survey and a velocity survey combined together. Many places I go now are also talking about point cloud data, where we're combining data from an ADCP with LiDAR data, with satellite imagery, and all that, and bringing it together in one package. Okay, there's a number of universities around, certainly in Europe where I mainly do my work, that are doing this sort of work, and they want to make it more, even easier to be able to do that. We need to consider the speed of data collection. Will the end user, will the customer, will the authority, the government be happy if we took a measurement in 1 minute? Will they say that is acceptable? Many people still look back to the International Standards Organization to sort of say, right, we need to have a standard for the way that we collect the data. Are we complying with the way that the data is collected? Do we want to do a traditional ADCP transaction, where we go from one bank to the other, do it 4 times, take the mean of the 4 to be our discharge measurement? Or maybe we want to sort of start, because we can collect all of this data, do a run-of-river measurement, where instead of going across the channel, we just go up and down the channel for tens, hundreds of meters, or even kilometers. It's a whole new way of collecting survey and discharge monitoring data. Gridded data. We see a lot of gridded data gets used in sort of rivers, but particularly in estuaries and lakes, reservoirs. Is there a GIS requirement? More and more people want to feed this data back into GIS systems. So, you've done all these checks on connections.
Why don't you go through this? This is more detailed.
Okay. So before we go out into the field, we want to do some pre-measurement checks. And I really do, I say do this before you go out in the field. It's really frustrating to be sat on the riverbank, okay, finding for some reason you cannot connect to the instrument. It's much nicer, much more leisurely to do it actually in the office before we go out. So make sure you've checked your cables and your connections really thoroughly. If there's a weakness in the system, these are a nightmare. The GPS cables, okay, they're just a standard RF cable, and you can, I'm not going to keep doing it too much because I'll break it, but we start to lose a connection in here. You don't want to go out to the field and find you can't get GPS just because you've got a bad cable. These cables you can get in any good store anywhere across the globe almost. So check those. The number of times somebody phones me up and says, the instrument's not working. All the lights are on the PCM. Connections are all look good. The cables are good. They're not broken at all. And this is the cable that links the PCM to the M9. And the only thing that they haven't done is just push this all the way in. They put that in, and they think if I just screw this up, it will pull it tight into the instrument. It's not designed for that. This has to be fully mated with its socket, and this one with its plug, before you start adding it on. Simple checks, but they will save you lots out in the field. Another thing just to, I put there, before power up, connect this cable, that to the M9 before we put the batteries in. There's a very, very slight chance, very small chance, but it is a chance. If you plugged it in this way, put the cable into the PCM, powered it up, had this end free, and this fell down into the water, we can get a short. It sounds obvious. I know of 3 people who've done it. This instrument is now, this is supplied last month. They've now secured against that happening. But on some of the older ones, there isn't the circuitry in there to stop that occurring. So just make sure you do the connection first. This is the latest generation of the PCM. On the older ones, which had a button on the top to turn it on, okay, there is also a little dummy plug that goes in. Again, ensure that that is put in if you're using the Bluetooth communications. That plug is not an antenna, as some people think it is. It's a switch. When it's plugged in, it routes the data to go out through the Bluetooth. If it's not plugged in, it's expecting the data to come out through the cable. Okay, so if you haven't got it in, you won't be able to use your Bluetooth. So here, this is that connector. When it's looking like that, it would be looking to send the data out through this socket down through a cable. Put a dummy plug in there, and it will come out through the Bluetooth, an internal Bluetooth there. Okay, as I said earlier, just check the integrity of your GPS cables. And something else that I don't know why it happened, I really don't know why it happened. It shouldn't happen, but experience tells me it does. The first time you connect to a PCM with a particular laptop, it seems to take a long time. I would just sort of say, just leave it, let it go through. It has an auto-detect where it checks through every port, it checks through every port at every baud rate. Just allow it to do that. And if after 5 minutes it's still not done it, then okay, then we need to look further. But once it's made that connection the first time, the computer recognises it and it routes it all quicker in future times. So the old PCMs, they use Bluetooth, okay, and we use a Pirani Bluetooth dongle for that. Some of them are the Pirani SD100, some of the Pirani SD1000s. The 1000s are slightly quicker, longer range and everything like that. Or we can go with the old PCM with a direct cable connect. If we have the PCM2s, It's the same frequency as Bluetooth, but it's actually it's different. It's just a 2.4 gigahertz data transmission. The reason we changed away from Bluetooth is on the Bluetooth we're getting a range issue and a data speed issue. We couldn't get at times enough data out over the Bluetooth back to the PC, particularly when we're at range. Okay, so they looked into new ways of doing that. You will notice that when you set it up that there are 3 transmit power levels with the new 2.4 gigahertz. With those transmits, you need to check what you're allowed to use as a transmit level in your particular country. Some countries are very strict on the amount of power that we're allowed to put out over 2.4 gigahertz. In the UK, we're actually only ever allowed to use the low transmit power, which reduces our range. I don't know what it's like here. Yeah, but at 2.4 gigahertz, sorry, I can't remember the exact transmit levels. It is in the manual, but
We have different power levels.
Power levels.
We can set the radios to low, medium, and high power. Every country has different requirements for.
It's a bit like the FCC in the United States will say, you know,
I think I don't think you have high power.
if you can use high power, great. You can transmit further. You'll get sort of up to 1.6 kilometers with line of sight. The only problem with using Bluetooth or add this 2.4 gigahertz, both of them are 2.4 gigahertz, is that water also has a frequency of just around 2.4 gigahertz. So if we put an antenna close to the water, that will be absorbed, the transmits and receive will be absorbed by the water and we will lose range. So the benefit is what we want to try and do is raise the antenna as high as possible above the water, and the amazing difference is the higher you go as to how much further. Just by putting it, instead of it, if we had the PCM directly on the board here and the antenna out the back of the PCM, just by raising it up about 40 centimetres, we can get half as much range again. So certainly think about doing that. Yeah, this is just a little hint. You know, if there's any communication problem that you had, or your PC goes to sleep while you've been doing something like that, it may be necessary to recycle the power to the USB. Okay, or serial adapter. I definitely have it on this computer. It's something the way that the computer handles its power out through its COM ports, and it shuts it all down to try and save power saving for the PC. If that's still unsuccessful, then sort of consider a reboot on the PCM. We do strongly recommend that on a monthly basis, I personally always do on a monthly basis, that you do a format of the recorder on the instrument. Okay? The instrument, every time it's collecting data files, okay, we have an 8 gigabyte recorder inside the instrument. You might think, when you look at the files, you might see you might have 500 megabyte files, you might have a couple of 500 kilobytes, a couple of megabytes, whatever. Those are the typical size. You might think, oh, 8 gigabytes will go on for forever. But actually what the instrument is doing in the background, it's also collecting an awful lot of diagnostic data. Those diagnostic data are a magnitude greater in size than the data files that you will be using. And they are filling up the recorder. Okay? So you might think you've got an empty recorder or plenty of room, but definitely, once you format it, it clears all those diagnostic files away, and then we can start getting quite confident. Those diagnostic files are there for good reasons. If you do have a problem with the instrument, okay, don't format it, if anything like that. we can send it all, we can send the instrument back, and then the engineers back in San Diego can look at the diagnostic files on the instrument to sort of get a hint as to what's been going wrong. But of course, don't format your report until you've downloaded your data. A couple other just practical things. We have 3 file types that are generated by the instrument. We have a .riv file. The .riv file is the file that is stored on the instrument. Even if we lose communication with the PC, okay, the instrument continues working and collecting the data. Okay? So we could have lost, maybe that battery's gone on the PC. You've started your measurement, you're going across, halfway across the river, your battery goes on your PC. Don't worry, just continue your measurement to the end, and when you get to the end, just take the power out, pull the batteries out, disconnect the cable, whatever way you want to, and that will close the file on the instrument. Okay, then when we're back at the office, we can download that file from there. We will need to add in our edge distances, but you will have your complete data file still on there. The .riv file will be that one. The data is also being transmitted through the radio back to the PC. If you have a complete data set that has been transmitted, not 1 second of data lost, okay, on the PC you will get a .rivr file. That is a mirror image or an exact replica of the .riv. But it just, when we see .rivr, we know that it's a PC file. If we've got .riv, we know it's off the instrument. The third file type is if we're collecting the data with the PC and we lose 1 second's worth of data, it will label that file as missing samples. That file, although it has missing samples, is actually still usable as a river discharge measurement file, as long as you had communication with the instrument when you stopped the measurement. Okay? Because every 1 second, what the instrument is doing, as well as sending all of the data, it's also sending a summary to the PC. And that summary has got the key things like distance, depth, velocity, discharge. Okay? So although the file is missing some data, the actual discharge value at the end is still correct and usable. But it's just sort of recommending that for that one, that actually you go back to the instrument and download the .riv file. And that's what I certainly recommend. You went through compass calibration? Yeah.
You want?
We'll do a compass calibration. So we're talking about compass calibration, setting the system time, some beam checks, the system test, whether we use RTK GPS or differential, and other GPS. The compass calibration is performed prior to every measurement, every site. I'd have to put my hand up and say I do not always do that.
We could do a direct connection. We don't need to have a box.
Now, yeah,
We could just, David, we could do a direct, no need to be
Oh, okay. Yeah, sure. So you also need a power?
yeah.
Sorry.
Do you want to be doing that? And I'll we should be doing a compass calibration at every site because the magnetic field will vary for every point on the planet. Okay? So we should be taking those errors that would be in the compass out. I know some people find it a real, pain to do that at every site. And I know some users go to a site where there is really low magnetic interference. They go out in the middle of the field where there's no metal or anything like that, and they will do a perfect compass calibration on the instrument. The instrument always retains its last compass calibration. And if that was a perfectly good one, they take the opinion that they can use that. The compass calibration actually does a little bit more than that, though. That's the problem with that process. It actually checks for what they call hard iron and soft iron situations at the site. And it will very slightly change that calibration. It's a sort of good time to talk about magnetic declination as well while we're here. Because, as I said earlier, everywhere on the planet we have different magnetic interference or magnetic fields going on. Okay, there is this property that we call magnetic declination. If we are using a GPS as well, then we have to set this declination. We'll come back to that. But we've set magnetic declination here on the smart page. Just type it in there. And to do a compass calibration, click on compass calibration, a new window will come up. And we'll go ahead and do that. It is. We actually, how many months ago? 6 months ago? About 6 months ago, we designed a new compass to be able to give us really good real-time feedback on what's happening in the channel. Okay, that wasn't possible with the old compass. We can still do the calibration with the old compass, but this ability to have real-time feedback wasn't there. So we've changed that. The same software detects what type of compass you've got on there. So when you click compass calibration, you will get different window come up. So this is the latest generation of compass. The procedure is really quite straightforward. We will click the start button down in the bottom left. We will do 2 complete revolutions. I'm still not. There are good grounds for doing 1 revolution clockwise and 1 revolution anti-clockwise. Okay? To help with the overall calibration of the compass. We used to say 1 minute, about 1 minute for every rotation. 1 minute for 360 degrees. With the new compass, we don't have to. We can do it much quicker. Okay. If you're using the old compass, if you don't see this little dialog box come up, it's the older compass. So that we still recommend 2 minutes for your 2 revolutions. We should also make the pitch and roll on the compass, okay, as we're doing that. And that pitch and roll should be to the amount that the instrument is going to pitch or roll in the channel. Okay? If we don't do it sufficiently, okay, if the instrument pitches or rolls greater than our calibration, then that data might be compromised out in the field. So, Mark. off you go. So you see it's given a start point here saying where it was started at, so around about 100 degrees. We can see the pitch and the roll being displayed on the screen. And obviously as we are going around, we can see the rotation of the instrument. It's good to do it nice and smoothly. Don't do it too roughly, too joltily. But we can do it, as I say, much quicker than we used to do. You should always do your compass calibration in the instrument that you are actually going to be measuring from. So although we're doing it here just for showing you how to do the calibration, actually, if you're using the trimaran, you should have mounted it in the trimaran. If this trimaran is going to be attached to a boat, we should actually attach this to the boat, okay, and then do the compass calibration in the boat, okay. That actually makes it quite difficult to do pitch and roll if you're actually in the boat. So all I would, the new compass is pretty good at doing a flat calibration as well. It's just that if then when we go up on the channel we're pitching and rolling a bit, then okay. Some boat handlers are very good at while they're doing the 360 degrees and actually forcing a bit of pitch and roll into the instrument as well. That would be helpful. Okay. Now I'm expecting this to fail in here, thinking that there's probably a bit too much metal inside the room. You might not.
On my mobile phone.
Yep, I was going to come on to that one. We should not have in our pockets any mobile phones, any keys. Okay, coins are probably okay. Unless you've got fake. Okay.
Let's stop it.
Yeah, so when we've got that, if I just click stop, and it will analyse that. Okay, and it comes up here, it tells us that the magnetic influence is unacceptable. Okay. The recommendations repeat the calibration where the magnetic field is uniform. You'll see here, this actual circle now is actually giving us a result.